The goal of this project is to model and analyze the thermal performance of a particular heat sink containing heat pipes. A series of wind tunnel tests were performed on a heat sink, and the results were compared with the output of a computer model of the same heat sink. This method resulted in development of a simplified method of modeling the thermal performance of heat pipes, along with a comparison of heat sink performance with and without heat pipes included. Over the last few years, consumers have demanded more computing power packed into smaller and smaller packages. In many cases, this has placed increased demands on the systems necessary to keep these products operating at safe temperatures. One way that the performance of standard cooling fins has been enhanced is through the use of heat pipes. Heat pipes are a hollow tube containing a liquid and a wick. At the heated end of the pipe, the liquid vaporizes, moves to the cooler section of the pipe, and then condenses. The wick then transports the liquid back to the heated end of the pipe, where it continues the cycle. Due to the nature of phase change heat transfer, heat pipes can move large amounts of heat from the generation point to areas where it can be dissipated. The complex interactions between the liquid, vapor, and wick within heat pipes represents a significant modeling challenge for those wanting to predict the performance of a cooling solution that includes heat pipes.
A wind tunnel was built using cardboard and a 120mm diameter 12-volt fan. Varying airspeeds were produced by adjusting the voltages to the fan from 6 to 12 volts. The wind speed was measured by using an anemometer, which provided the air velocity measurements in meters per second. Using the adjusted voltages, the tunnel produced air velocities of 1.2 to 3.4 meters per second. A constant heat flux of 25 watts was applied to the base of the heat sink by a hair straightener heating element. The base and ambient air temperatures were both recorded using thermocouples. One thermocouple was attached to the base without touching the heating element, while the other thermocouple was outside the wind tunnel. The model's control volume was set to the same dimension as the wind tunnel. The outlet boundary condition was set to the airspeed measured in the wind tunnel, while the inlet condition was set to zero gauge pressure and the measured room temperature. A constant heat flux of 25 watts was applied to the base of the heat sink. The maximum temperature of the heat sink base was recorded for each air velocity. Standard material properties were used for everything except the heat pipes. The heat pipe model was adjusted until the measured temperatures were within 2 degrees of the experimental values as seen in the graph. The heat pipe was modeled as a copper tube filled with a thermally conductive solid. The wall thickness for the heat pipe was the same for both the model and the physical pipe. In order for heat to move through a heat pipe, it must be conducted through a copper wall, move through a phase change process, then be conducted back through the copper wall again. This process is represented on the left as a resistance network. Because the phase change process is effective at moving heat, its resistance is very small compared to conduction through the wall of the pipe itself. Because of this, the heat pipe can be modeled as a copper tube filled with a highly conductive solid. This removes the need to model the phase change process in the simulation. The values depicted in the resistance network were used for this simulation. The left and right resistors represent the wall resistance. These use the thermal conductivity of copper, which was 400 watts per meter Kelvin. The center resistor represents the heat transfer occurring inside the pipe through the phase change process. In order for the simulated values to match the experimental values, the thermal conductivity of the solid inside the pipe was set at 370,000 watts per meter Kelvin. To investigate the effects of embedding heat pipes in this particular heat sink, simulations were run with and without the heat pipes included. As seen in the graph to the left, in all the simulations the temperature had a noticeable increase without heat pipes, with greater differences at lower airspeeds. After removing the heat pipes, the average temperature increased by 4.3 degrees Fahrenheit. The differences can be seen in the two figures on the right, where the top figure included the heat pipe while the bottom did not. In the figure with the heat pipe, the temperature is more evenly distributed across the fins, while the figure without shows higher temperature in the base of the heatsink. This project was able to develop a method for analyzing a particular heatsink containing heat pipes. It was found that heat pipes can be modeled with a highly conductive solid core representing the phase change process. It was also demonstrated that heat pipes are effective at balancing out temperature distributions in a heat sink. As modern electronics continue to advance, improvements in heat pipes and their associated models will be required to dissipate their increased thermal output.